So in the previous lesson, we worked extensively on converting from concentration of H+ to pH and vice versa. Before we get to the next topic of this lesson, which is weak bases and strong bases, I wanted to show you how to do that conversion using just mental math. Because if you are faced with a multiple choice question in which you're asked to determine the pH and you don't have a calculator, you need to be able to do that. So here I tell you that the concentration of H+ is 1.2 times 10 to the negative fifth. All right, so what I do I'm going to get a range for my pH. Obviously, I'm not going to be able to get an exact value. So I know that 1.2 times 10 to the negative fifth is greater than 10 to the negative fifth, right? Because 10 to the negative fifth, another way to write that is just 1 times 10 to the negative fifth. So 1.2 times 10 to the negative fifth would be greater than that. I also know that that is less than 10 to the negative fourth. All right, so that's not too bad. Now, how do I convert that into pH? Remember, to find the pH, I need to take the concentration and I need to take the negative log of that. So the negative log of 10 to the negative fifth is simply 5. And the negative log of 10 to the negative fourth is simply 4. So what that tells me is that my pH is going to be between 4 and 5. So my pH is greater than 4, but it's going to be less than 5. And that's all there is to it. Okay, let's look at another problem. So here I'm told my concentration of hydroxide is 5.6 times 10 to the negative 7, all right? So 5.6 times 10 to the negative 7th is greater than 10 to the negative 7th, but it's less than 10 to the negative 6th, which tells me that my POH is going to be somewhere between 6 and 7. Keep in mind it's POH because I'm using the concentration of hydroxide. So it's somewhere between 6 and 7, which means my pH is going to be somewhere between 7 and 8. Okay, and just to double check, I plugged these into my calculator. For the first one, the exact pH is 4.92. And for the second one, my pH is 7.74. Okay, so you can do mental math and determine approximately what the pH would be. That's going to become useful throughout the rest of this big idea.
So now that we've looked at weak acids and strong acids, we're now going to look at strong bases. Now, when we're doing pH calculations for strong bases, we don't have to use ice charts. So we don't have to use ice charts because 100% of the strong base is going to dissociate. However, I like to show the ice chart just because it makes it a lot easier for me. So I'm going to show the ice chart right now. Okay, so let's look at a problem. It says, what is the pH of a solution of 0.040 molar calcium hydroxide? Okay, so I'm going to show the dissociation of it. So it's going to be calcium hydroxide decomposes into calcium ions and 2 hydroxide ions. I'm going to create an ice chart. My initial concentration of calcium hydroxide is 0.040. The initial concentration of calcium and hydroxide are both 0. Okay, so the change, because this is a strong base, the change is going to be negative 0.040. The change for calcium is going to be plus 0.040. And then because for hydroxide there's a 2 coefficient, it's going to be plus 0.08. Okay? So at equilibrium, your concentrations would be 0, 0.04, and 0.08. Okay? To find the pH, since I have the concentration of hydroxide at equilibrium, I need to first find the POH. So the POH is going to just be the negative log of 0.08. So that gives me 1.10, which means the pH is going to be 14 minus that, which is going to be 12.90. The dissociation of weak bases. And in this case, a weak base is represented simply with a B. When it reacts with water, remember it's a proton acceptor, so it becomes HB with a positive charge, or hydroxide, because hydroxide lost its proton to the base. Now, again, just like with weak acids, we can write the equilibrium expression. In this case, it's going to be your BH or HB plus, so your conjugate acid times the concentration of hydroxide all over the concentration of your base. Remember again that water, since it's a pure substance, we don't include it in your equilibrium expression. And again, your Kb is now your base dissociation constant rather than your acid dissociation constant. So in this reaction, I have ammonia reacting as a base. Therefore, in this reaction, I have ammonia as my weak base reacting with water, which is going to serve as my acid in this problem. Remember, double arrows because it's a weak base. Ammonia is going to accept the proton that water gives it, so it becomes NH4 with a +1 charge, and water loses its proton, so it becomes hydroxide. Now this problem is now going to be identical to the weak acid problems we previously performed. So I got to write out my ice chart. I have a concentration of 0.15 molar NH3. Remember, since this is a pure liquid, I'm actually not going to be looking at water at all, so I can just ignore that. I start with no ammonium and no hydroxide. I do know that the change is going to be -X for ammonia, so the equilibrium concentration is going to be 0.15 minus X. I know that this is going to be plus X, and this is going to be plus X here. And so my equilibrium expression is going to be X times X, which is X squared, all over 0.15 minus X, and I'm going to set that equal to my Kb, which in this case is 1.8 times 10 to the -5th. I'm going to assume that my X is small enough that it won't affect my equilibrium concentration of NH3, so I'm going to ignore it to make my life easier. So X squared equals, when I multiply 0.15 by 1.8 times 10 to the -5th, I get 2.7 times 10 to the -6th. Okay, and then I need to find the square root of that, so my X is going to end up being 1.6 times 10 to the -3rd molar. And so this is actually going to be my concentration. My X is my concentration of my hydroxide ions. And so what I can actually do is I can take that and plug it into my formula for POH. I'm going to find the negative log of the 1.6 times 10 to the -3rd. Okay, and when I do that, I find that my POH equals 2.8. Now, I'm actually not interested in POH. I want to find my pH. So 14 minus that value gives me a pH of 11.2. And that is my final answer.